Network layer. Message at physical layer is called as bits, whereas at data link layer it is in form of frames, and at network layer it is packets or datagrams. Network layer is primarily concerned for moving data from point A to point B. Although this seems simple at first time, it can get quite complex as you begin internetworking over complex WANs. Remember one thing is that network layer is only concerned with getting the datagrams to their destination. In general, network layer has four functions: 1. Logical addressing, 2. Switching, 3. Routing, and fourth is network control. Logical addressing. In general, addressing distinguishes one location from another. That location can be a home, network device, or anything. Data frames need addresses so that they know where to go and what to do. Addressing works on hierarchy structure. In network world, each data frame needs three addresses: 1. Physical address, 2. Logical address, and third is service address. To reach your data at correct device, it must include three pieces of information. First, your data frame must include a physical address. This physical address is 12-digit hexadecimal ID programmed onto the computer's NIC at factory. If your network is very large, you will need logical address to narrow down the search. This address is programmed by you at network layer. Finally, each data frame needs a service address so that it can find appropriate destination application. This address operates at transport layer of OSI reference model. Switching. Most large internetworks consist of multiple physical paths between the sender and receiver. Intermediate routers are responsible for moving packets across these diverse links, and switching makes this possible. Note that at switching, we are not choosing any path. Routing takes care of that. In short, switching is simply the fundamental architecture that allows us to use one or more of these paths. There are three types of switching in network layer: 1. Circuit switching, 2. Message switching, and third is packet switching. Circuit switching. Circuit switching connects the sender and receiver by a single path during the duration of conversation. For example, telephone switching equipment uses address numbers to establish a path that connects the sender's telephone to receiver's telephone. Once the connection is established, a dedicated path exists between both ends until the connection is terminated. Circuit switching in computer networks operates in the same way. A complete end-to-end path must exist before communications can take place. The computer that initiates the data transfer establishes the dedicated path at session layer and ensures reliable packet delivery at transport layer. The network layer is responsible solely for moving datagrams along the circuit. Message switching. Message switching does not establish a dedicated path between two stations. Instead of this, conversations are divided into messages. Each message is packaged with its own destination address and then transmitted from router to router through the internet. Each router receives the message, stores it briefly, and then transmits it to next device. This type of network is sometimes called as a store and forward WAN. Packet switching. Packet switching combines the advantages of both circuit switching and message switching. Packet switching breaks datagrams into small parts called packets. Each packet is constructed with source and destination addresses so that it works through internetwork and find its destination. Because packets have strictly defined maximum lengths, they can be stored in RAM instead of on disk. This makes store and forwarding faster and easier. Packet switching router uses two different strategies. One, datagram packet switching, and second is virtual circuit packet switching. Datagram packet switching is similar to message switching, in which each datagram has various paths to choose from. Datagrams flood the network channels and find their way to receiver using various paths. These paths are determined using intelligent routing mechanism. Once datagram arrives, they are reordered according to sequence number. Virtual circuit packet switching. Virtual circuit packet switching relies on a logical connection between sender and receiver. The connection is formed when devices exchange messages at the outset of a conversation. These messages allow the sender and receiver to agree on conversational parameters including message size, path to be taken, and conversation length. This strategy is almost like circuit switching. The difference is that virtual circuits can be temporary. Routing. I can say the real purpose of OSI networking is routing. Routing allows intermediate network devices to make intelligent decisions about how the message should travel from point A to point B. Routing involves two simple steps. One, route discovery, and second is route selection. Route discovery. Before we can choose the optimal route, we need to discover all available options. That's the purpose of route discovery. During route discovery, the internal routing information protocol, that is RIP, builds route information table, that is RIT. This RIT lists all possible paths from the router to a given destination. Each router builds its own table and modifies it continuously as needed. Every RIT is made up of three important components. One, network addresses. Second, next hop to reach the destination LAN. And third is cost to reach the destination LAN. There are two most popular route discovery methods. One, distance vector route discovery, and second is link state route discovery. Distance vector route discovery. Distance vector routers compile and send RITs to all routers on their segment. Each router builds its own table and updates continuously from its neighbor. Link state route discovery. Link state route discovery relies on global broadcasts. Each router identifies its own segment by sending out a message to all routers on the internetwork. This initial message contains information on the state of the router's own LAN. This way, each router initially builds a complete RIT, which is updated only when changes occur. Each router broadcasts changes to global RIT, and other routers modify their own tables. Once we have built our RIT, we have complete lists of all hops between our network and the destination network. These paths also valued according to time and cost information. Route selection. Once a router has built its RIT, it can use cost information to calculate an optional path, that is the interconnected combination of routers that require the fewest hops, ticks, and expense. Route selection has two approaches, one dynamic and second is static. Dynamic route selection uses internal routing algorithms to gather cost information continuously. Every packet is assigned route depending upon the latest discovery cost. Multiple paths may be used to send packets between two devices depending the changing nature of the network. In addition, route selections are made at every router in the network. That means any router along the way can change the path. Static route selection. Static route selection is based on a predetermined path. Every packet must follow this path and every router must make selection decisions based on the path. In static route selection, only the system administrator or initial router can choose path. Network control. Network layer has some administrative tasks that supports internetworking and routing. These tasks ensures a steady speed and rejoin with all the rest of the datagrams at the other end. These tasks includes 1. Network flow control, 2. Network sequencing, and third is network error checking. Network flow control. Network flow control monitors the amount of data that follows any specific path in the network. With network flow control, transmission speeds and network reliability can change from one moment to the next based on the amount of traffic being generated by all senders and receivers. Through internal administrative mechanism, the network layer can control the amount of data sent on given route and provide alternate paths for certain packets. This function is called congestion control. Just like flow control at data link layer, network layer flow control can be performed by negotiation of guaranteed rate or through static or dynamic windows. Network sequencing. Network sequencing reorders packets once they arrive at the destination device. Network sequencing uses two pieces of information, one datagram ID and second is sequence number. The datagram ID identifies pieces from the same packet. These addresses allows datagrams from the same packet to be grouped together. The sequence number then provides ordering for different datagrams within same packet. If datagrams arrive out of order, The destination device reorders them according to datagram ID and sequence number information. This type of network layer administration is required for packet switching network where datagrams routinely arrive out of order, and it may also be necessary with large virtual circuit networks. In virtual circuit networks, an error can occur when one link fails and new one is set up in the middle of a transmission. In this case, we need to piece them back together at destination. Network error checking. Error checking occurs at three different layers: data link layer, transport layer, and session layer. Network layer error checking works in conjunction with the transport layer. It is concerned primarily with packet loss, duplicate packets, and or altered data. This ends our network layer functional overview.